All right, I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just pray that you'd help us to understand a little bit more about the spectral theorem and just to wrap up our thinking about chapter 4 at the moment, Lord. In your name I pray, Lord Jesus. Amen. So yeah, what my goal is to try to say something cogent about eigenvalues and the spectral decomposition. And I may even take a shot at proving the theorem today. We'll see what happens. I reserve the right to bail on it. But here we are, section 4.10, spectral decomposition. In my, what I'd really like to do is only do about maybe 20 minutes on this and then spend the rest of our time trying to solve a differential equation. That's what I'd like to do. So we'll see how that goes. Theorem. This is the Hilbert-Schmidt theorem. All right, so it says, well, his preamble to it is if H is a finite dimensional Hilbert space, say complex n vectors, it's known from linear algebra that the eigenvectors of a self-adjoint operator on H form an orthogonal basis of H. The following theorems generalize this result to infinite dimensional spaces. So here it is. For every compact self-adjoint operator, compact self-adjoint operator. So I know we're kind of working in a weird space in this class at the moment because I haven't really given you a proper definition of compact operator or anything, right? We haven't really delved into it, but I'm nevertheless trying to give you a sense of what it accomplishes, you know? So we're kind of in some sense in a partial survey mode here, right? So self-adjoint operator A on an infinite dimensional Hilbert space H. All right. There exists orthonormal system of eigenvectors. All right. He calls them UN. All right. Corresponding to non-zero eigenvalues. Lambda n, such that every x in H has a unique representation x equal to the sum n equals 1 to infinity of alpha n un plus, let's say, nu, where alpha n are in C and nu is an element of the null space of A. Now he doesn't call it null A. I'm calling it null A. He gives a scripty n kind of thing there. All right. Now let me pause and think about my life. Whether or not I want to commit to doing this proof. All right? Let's see here. It is 2 pages. That definitely will go counter to my purpose of just spending 20 minutes. Let's see here. Let's look at the proof here. So he begins by using theorem 4.9.16 and corollary 4.9.17 to find the existence of a first eigenvalue. And then, all right, well, let's trace through some of the steps just to gain a sense of how it's done, yeah? So the proof, I will tell you some things about it. So he begins by, there exists eigenvalue lambda 1 of A such that the modulus of lambda 1 is the supremum over the unit ball of the absolute value of the inner product of AX with X. All right. And then he says, let U1, basically let AU1 equal to lambda 1 U1, and the length of U1 be 1, okay? Set Q1 equal to X in the Hilbert space such that X is perpendicular to U1. All right. In other words, Q1 is the orthogonal complement of the set U1, thus Q1 is a closed linear subspace of H. All right. And then if X is an element of Q1, what can we say? Then if we look at the inner product of AX with U1, what do we get? Now, how does he move the A to the other side, guys?
It's self-adjoint.
Self-adjoint, right? Self-adjoint. But remember, it's an eigenvector with eigenvalue lambda 1, so we get lambda 1 conjugate XU1. But of course, I mean, he doesn't even have the conjugate, and why is that reasonable?
That's not sure.
Yeah, because this is self-adjoint, right? We prove the eigenvalues are
Real.
the real, right? Real. So, but then by construction, this is what? X is perp to U1, right? So this is equal to 0. All right. So then what? So that means that thus AX is also an element of Q1, right? See that X, we're assuming X is an element of Q1, but we've just now proved that in fact also AX is an element of Q1. Therefore, A maps the Hilbert space Q1 into itself. And that means we can again apply, we can apply the corollary and the theorem that started the proof once more to get an eigenvalue lambda 2, right? So in other words, this means thus, you can look at, you know, A as a mapping from Q1 to Q1, right? In other words, you can, well, I mean, A is not that mapping, technically speaking. It's a restriction of A that we're talking about. But with respect to that restriction, it's the restriction of a self-adjoint operator, self-adjoint. And as such, we can apply the initial step again. And so there exists eigenvalue lambda 2 of A such that the modulus of lambda 2 is equal to the supremum of, let's see here, what would the context be now? Norm of X less than or equal to 1, supremum AX, comma X. But there's more than that, right? This is for X and where? A little more fine print here. Well, he writes it this way. He puts a curly bracket here, right? And he adds another condition off to the, I mean, you got notational choices here. Some people would just tack on down here x is an element of Q1 and just start stacking conditions. The other option is to write it as a set, and then put over here x is an element of Q1. So whatever notation floats your boat, I suppose. The point is, it's the supremum of the inner product of AX with X, where X is taken over the unit ball intersected with Q1. Yeah, and then you let Q2, so, define, AU2 equal to lambda 2 U2, with norm of U2 equal to 1. The existence of that is given by the theorems mentioned at the top, theorem 4. As he says, theorem 4.9.16 and corollary 4.9.17. Which I think we talked about last time, actually. And anyway, so now you build Q2 in a similar fashion, Q2 equal to x an element of Q1, such that x is perpendicular to U2, I believe. All right? And then you can repeat the above argument. So then you can argue that A does what? It can also be takes Q2 to Q2, right? And we can just keep recycling this argument, right? And he says you can recycle it, and you get eigenvalues lambda 1 through lambda n, and corresponding normalized eigenvectors u1 through n, and each time define Qn. Qn equal to what? Equal to, x in Qn minus 1, such that x is perpendicular to, apparently, un, right? Where you have eigenvalues lambda 1, lambda 2, dot, and u1, u2, dot.
Can you move me when you get a sec?
I will do that. Whoa, whoa. Whoa. That good?
Yeah.
Okay. It's okay, I'll fuss with it. I'm going to leave it kind of halvesies at the moment. Okay, then what? Well, let's see here. He says choose an eigenvalue lambda n plus 1. For un plus 1, we choose, okay. All right, well, I don't know what I don't understand what he's saying. I guess he's just, oh, okay, fine. So what's lambda n plus 1 going to be equal to? It's going to be the supremum, right, over the norm of x being less than or equal to 1 of the modulus of ax x such that x is an element of Qn, right? All right, great. That's his equation 4.40. And then for un plus 1, you choose a normalized vector corresponding to lambda n plus 1. All right, fine. This procedure can terminate after a finite number of steps. Indeed, it can happen that there's a positive integer k such that ax is equal to 0 for every x in qk. So then, if there exists, k in the natural numbers such that the inner product of ax with x is equal to 0 for all x in qk, right? that could happen, right? And if that happens, then that means that lambda k plus 1 does not exist, right? Does that seem fair? So like if this is, well, how can I say this? That's not quite the right thing to say. I mean, I don't know, there's different ways you could look at it.
Well, we're structuring Q sub in a set of the orthogonal complement of something. So we're not. If that's the case, I guess we're not pulling from anything.
Well, I guess I'm saying, I mean, you could still have the eigenvalue be 0, right? I mean,
Oh. But the supremum of that set doesn't, of the set would be constructing what it exists. Because we're.
oh wait a minute. If there exists a positive integer k such that ax with x equal to 0 for every x in qk. Okay, yeah. Well, anyway, let me just. That's not so much interesting. Whether or not we want to quibble about how to label the results, let's just say that means that x is equal to alpha 1 u1, alpha 2 u2 plus da 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 plus alpha k uk plus v, or I'll call it nu, where
Isn't that what we're trying to get?
yeah, that is what we're trying to get. I'm just trying to understand why that's the next step here. I'm trying to understand why that is. Then he says then every element of x, every element x of h has a unique representation like that.
Yeah.
I mean, I'm not thinking.
Would that be because since it's finite, we have an orthogonal system, and since therefore it's narrowly independent? I don't know where the.
Well, he says, I mean, this is where a nu is equal to 0. And of course, the u1 through uk are respectively the non-zero normalized eigenvectors, respectively, for lambda 1 through lambda k, which we use to set up the q sub 1s through q sub k's. Everything has been like pretty straightforward to me up to this right this step, and I'm.
For every x in qk for qn is the orthogonal, it's perpendicular.
Oh, just.
It's perpendicular to
Oh, and then he's like, in this case, notice that ax equals to what? Ax equals 2, you know, when you apply a to this formula, what do we get? We get, you know, lambda 1 u1 plus lambda 2 u2, right? Lambda k uk, and then it sends that to 0, and I think that was well, yeah, I mean, that's right. So if this happens, Audric, then we're in the finite case, right? In that case. But on the other hand, if the described procedure yields an infinite sequence of eigenvalues, lambda n, and eigenvectors un, then he's like, let S be the closed space spanned by the vectors, and then he uses theorem 3.66 to decompose every x and h as a sum of the, there's a part of it reached from the orthonormal system, and then there's something in the null space of A. There's something in the perp to this S. The S is the closed subspace spanned by the orthonormal system. And then he has about a half page here that proves that you still have it takes him about a half page to argue that if that is how nu is constructed, then you also have that nu is in the null space of A, follows from it being in the perp of S. Oh, that's cool. Oh yeah. Oh, yeah. This is all right. So I'll let you guys read that other half of the page for yourself. Let me instead talk about finite dimensional linear algebra for just a second here. So what's being generalized, I believe, is this. So you can talk about the fundamental subspaces for a linear transformation, right? And so if you think, you're fine, I got it. If you think about, so just to recap the proof of the theorem, basically what I have on the board is the finite. If it truncates, then you have a finite system. And so this infinite series in the theorem just becomes a finite sum. Otherwise, it goes on and on. You get an orthonormal system. You take the take the span of that system, form a closed set from that. You use an orthogonal complement theorem from earlier in the book to look at the perp to that closed system, and then you argue that things in the perp to the closed system have to actually be in the null space of the operator, in the kernel of the operator. This null, listen, so like, just a second here. So if I have a linear transformation T from, let's say, I don't know, a vector space V to a vector space V, right? Then, whoa. What happened, Audric?
Oh, I accidentally did the blur thing, and now I have this thing. Now I have these glasses on.
All of a sudden, I look back, Audric's got the, like these, early 1990s, like, digital glasses on. That's very cool.
Nice.
I was trying to mute myself, but I gave myself glasses.
I need to get the next camera I buy, I want it to be able to do that like real time in a lecture, you know?
Let's see.
All right, so listen here. So of course we have kernel T.
There we go.
Would be x in V such that T of x is equal to 0, right? And you also have the image of T is equal to T of V, right? Okay, so if you say that the matrix of T, let's say, is equal to A, let me suppress my desire to talk about the basis forget about the basis, right? Just there's a basis and stuff we should talk about, be more careful. But there is a matrix of T, it's A. So with respect to A, you can talk about the null space of A. So this is the language I typically use. So I keep it real. So x in Rn such that Ax equal to 0, yeah? In the column space of A is, basically Ax such that, x is in Rn. But this is also equal to the span of the columns of A. So let me talk about this a little bit more. If we have a set of vectors, right, S, say S1, S2, Sk, then you can take a set of, and this is a set of column vectors, all right? You can concatenate these, put them into a matrix like this. All right? Like that. And I usually call that the matrix of the set. All right? So one of the things I could tell you is like the span of S, all right? It would be the column space. I try to use capital C for column space of the matrix of S, all right? What would the perp to S be? What is the orthogonal complement with respect to the Euclidean, the usual dot product in Rn, S perp? So what you're looking at is X in Rn such that what? Such that X dot Si is equal to 0 for all I, right? But let me put these up here. So like X dot Si is actually,
But it's for all I, it's just, it makes up the
I
set.
ran out of camera space.
oh,
For you, Jim.
The big ones just be the equivalent.
There we go.
so, I mean, maybe I'd do better to write it like that. So what you're looking at is Si transpose times X. So, and you've got this, you know, you got a stack of the,
Sorry, I didn't quite catch that. Could you please say?
I'm so sorry.
you're fine. So we've got, you know, X dot S1 is this, X dot S2 is S2 transpose X, X dot SK is SK transpose times X. You've got this stack of equations. You can put them all together and simply write that the transpose of S times X is equal to what? I buried the lead here, right? I mean, these are perp equations, right? So X dot S is 0. Every one of these is 0. 0, 0, 0, 0, 0. So you see this short calculation shows you that the perp of S is actually the null space of the transpose of this matrix. And I think in some sense what this proof is doing is giving you an infinite dimensional analog of this. Like the second half of the proof, I feel like it's essentially that, because he's joining the perp to the set. Like his set is the set in the second half of the proof. It's the closure of the span of the orthonormal system built from the eigenvectors U1 through UN and so forth and so on forever and ever, amen? So he's closed the perp, and then he's arguing that those things are also in the null space of the corresponding matrix. And you notice that this would be, I'll miss it, one other thing here. Golly. Well, anyway, it's a feeling I have. I'm not saying something rigorous. I feel like there's a connection there. I could be wrong. I'm just spitting into the wind here. But all right. Well, anyway, the next theorem is the spectral theorem for compact self-adjoint operators. And he says, let A be a compact self-adjoint operator on infinite dimensional Hilbert space H, then H has a complete orthonormal system consisting of eigenvectors of A. Moreover, for every X, you can write that. What's the difference in corollary versus the theorem? Compact self-adjoint operator. Didn't I assume it was compact and self-adjoint last time?
Yes. But the punchlines are different.
Yeah. For every compact.
Oh, I think that, doesn't that just come from, like, in the finite case, we just applied?
Oh, is it finite dimensional?
Yeah, no, it's, no, in the proof of the previous one, we just applied A and got rid of that V in the null space of A. So, like, if you see on, page 197, 4.3.
Oh, oh. I'm an idiot. Yes, thank you. Yeah, I'm making a mountain out of a mole. I don't know. Pick your favorite euphemism here, but yeah. I'm just dumb. You just take the previous theorem and let A on this, right? Oh, I'm sorry, Audric. Here, I'm gonna put you back in your previous table. I hope it's okay. Is that okay?
Fine.
Okay,
Just
cool.
gotta tilt me up. There we go. Maybe move me a bit over to my right. I don't know which way.
Is that good or no?
A tiny bit more that way. That should be fine.
Okay. So all I was saying is it's just like Jacob was saying, just multiply this by A. See, AX, it's just that. That's the corollary. AX is equal to.
Just because you get the lambda out.
Right. You get sum n equals 1 to infinity of lambda n un, and then plus a nu, but this is 0, right? And then more than that, the lambda n is it's more than this, right? The lambda n's are actually what? They're actually given by the oh.
There's a little more details to it.
Oh yeah.
Saying, take the arbitrary orthogonal basis of.
Oh, okay. I know what's going on here. I can explain. There is a little bit more that's going on here. My bad.
Oh, sorry, I wanted to simplify.
Well.
Oh, it's a Hilbert space, so it's complete. And so.
Oh, was it not a Hilbert space before? What was a Hilbert space before? No, it is. It is a. It is a corollary. So his proof here is he's like to obtain the. So the thing is that the Vn, our orthonormal system for H. And let's see here. Let me just read his corollary proof. We need to complement the system U1 through U2 defined in the proof of the theorem with a arbitrary orthonormal basis of the null space of A. Of course, what is the, are these eigenvectors? Well, yeah, because A nu is equal to what? 0, right? So those are also eigenvectors with eigenvalue 0. And so essentially, I don't know, you can kind of think of this corollary in this sense. You take these guys, right? And then you just adjoin to them an orthonormal basis for the null space of A, which has to exist because, again, A is self-adjoint. This is a subspace of a self-adjoint. You could think about the restriction of A to the null space of A. You'd have a self-adjoint operator on a Hilbert space still. And so, yeah, there exists an orthonormal system that forms the basis for there. So you take that one and join it to the one you already have, and then you got an orthonormal system for the whole deal with this equation. So, and then his corollary 4.10, this is corollary 4.10.2 is this one. And then his corollary 4.10.3, give me a second here. Whoa. Oh, I thought the whole page was a proof of corollary. It was not, though. Oh, man. Let's see, what's he got? What we got here? We got corollary 4.10.3. A compact self-adjoint on a Hilbert space H, then A is equal to the sum. Oh, you can build it from a series of projection operators where the weights are the eigenvalues. Projection on, a finite dimensional subspace of H. Really? Is that right? Huh. That's surprising to me. The reason it's surprising to me is one of the eigenvalues could be 0, right? No? Compact self-adjoint. Yeah, I mean, you can have 0 eigenvalue, right? Huh. Huh.
They have 0. Wait, but I mean, like,
Oh, right.
like, yeah, the simplest it could be is the identity, right? Like, it's the simplest self-adjoint operator that's compact.
I mean, yeah, so my bad. So what I'm forgetting is, like, in principle, there's also plus 0 times pi, let's say, right? Where pi is a mapping from H to, like, I don't know, the null space of A, right? But that doesn't appear in the formula. Like, this is not saying that the null space of A is necessarily finite dimensional. That's what I was trying to make it say, and it doesn't say that. Because this doesn't give you, this formula doesn't indicate anything about the 0 eigenspace, right, Audric? Because, like, the lambdas are, the proof says they're non-zero. Well, he says let lambda 1 through lambda, the second half, he's like, another way of representing A in the form 4.42, let lambda 1, lambda 2, be all the non-zero eigenvalues of A. All right. In any event. He says corollary 4.10.3 is just another version of the spectral theorem. It says it's important because it has natural extension to more general class of operators, and it's useful because it leads to an elegant expression for powers of other functions of an operator. Yeah. Oh. Yeah, let's talk about that. So what's now? I know we haven't really delved too deeply into the projection space. So let me not fuss about this here. That's kind of not interesting. I just got stuck up on. It seemed contradictory to me to, like, like I said, I wanted that to say the null space is finite dimensional, which didn't seem to make sense to me in the abstract. Okay, so the thing about a projection operator, right, is what is Pn times Pn equal to? So, like, not an identity, but Pn again. The thing is, they're idempotent. So if you take the shadow of the shadow, basically projection operators they project a shadow of a space onto the subspace to which they're projecting. And so, and this generalizes, right? So if you have like Pn to the power k, it's Pn, right? So the cool thing is, if you look at a squared, right, you've got what? Some n equals 1 to infinity of, lambda n Pn. And I can do that, a times that, right? So if you just think about, oh man, that's not the right way to think of it.
That's what
Well, that is what he wrote, isn't it?
I think it's just passing like a through since we're considering linear operator.
Okay. Well, I guess that is what he does. I couldn't see it. N equals 1 to infinity of lambda n apn. All right, so I guess we have to feed it a vector. Apn acting on x is, ax. Well, good grief. It must be that the projection operator commutes with other operators. So anyway, I'm not 100% sure the step I'm writing down right now is right, but I do know what follows after it is in the book, and it seems totally reasonable. So that gives me Pn lambda x, right? Well, goodness gracious. I'm still not being clear here. Why? Oh. Sorry, guys. Being too hand wavy here. Let me drop back to finite dimensions for a second here. If you have an eigenvector, AU equals to lambda u, right? And you multiply both sides by A, what do you get? Right, A squared u equals to lambda squared u. So, if I have, sorry, I'm trying to think of how to sort through this. Well, let me just look at the, sorry guys, there's something here I don't know. Well, let me not torpedo this lecture. Let's keep going here. So this is the sum n equals 1 to infinity, as he points out, lambda n squared Pn, right? That's what he argues. He says that's because APnx is equal to lambda n Pnx for every x and h. So all right. Gah. fine. A equals to lambda 1 P1 plus lambda 2 P2, okay? Let's think about just two of them, all right? Where here I'm building P1 and P2 like I did the other day by the outer product of the vectors, you know, you could do that. You know, like P1 could be U1 transpose, is it? Yeah, U1 transpose and such. So if I square this, I have lambda 1 P1 plus lambda 2 P2 times lambda 1 P1 plus lambda 2 P2. And I get like, you know, lambda 1 squared P1 squared plus lambda 1 lambda 2 P1 P2 plus lambda 2 lambda 1 P2 P1 plus lambda 2 squared P2 squared. So I think the result I'm stuck on, it's because we didn't get into the nuts and bolts of that section we skipped. That's what I'm getting hung up on here, Audric. Because there is something non-trivial. I mean, even in the finite dimensional case, why are these 0?
The alpha and PNs?
Yeah, like the P1, P2, and the P2, P1, why are those 0? I mean, if you think about them, in terms of explicit matrices I built them from, P1, P2 is something like U1 transpose times U2 transpose. Now here I'm assuming very simple case that the eigenspaces are one-dimensional. Generally speaking, you'd have to build it from a sum of these kinds of things for like a, you know, a higher rank eigenspace, but that's 0. So these are both 0. And then P1 squared is P1, P2 squared is P2, so you get like lambda 1 squared P1 squared, P1 plus lambda 2 squared P2 squared. P2, no square here, yeah? Which is the finite dimensional analog of that theorem. So there is, as he says, you can show that A Pn x is equal to lambda n Pnx. And because that's true for all x, you go from here to here. All right, I think I said enough about it. Now, if this is true for the square, it's just as well true for the power. So if you have, you know, like, let's say f of t is equal to, say, a0 plus a1t plus plus ak t to the power k, like a polynomial, right? Then if you look at f of a, you can build it as the sum n equals 1 to infinity of lambda n. Let's see here. F of Pn, I believe.
I think you got it backwards.
I do? It's possible.
Yeah.
They say constant values with eigenvalues.
Oh, eigenvalues. Oh, yeah. Thank you. That makes more sense. Duh. Like something feels wrong here. So that should be f of the eigenvalues, right? Times Pn. There we go. That makes more sense. And there's no infinity here, right? Here I'm just n equals 1 to k. But if we go to the next page of the book, he'll do the same thing for like the Maclaurin series for sine or something, right? So you can take like the sign of an operator in this way. And the sign of an operator is, you know, defined to be in terms of this series of projection operators with the weights given by the, you know. Yeah. So yeah, that's his definition, 4.10.4, function of an operator. You know, for a compact self-adjoint operator, we define f of a to be, you know, sum n equals 1 to infinity of f of lambda n Pn. So basically he makes a definition. He turns this into a definition for the function of an operator. Yeah. All right. Now theorem 4.10.8, for any two commuting compact self-adjoint operators A on a Hilbert space H, there exists an orthonormal system H of common eigenvectors of A and B. You know, that's going to be important to us when we look at quantum mechanics, right? So, all right. Now the next section is on unbounded operators. I don't really think I have anything much to say about that, except that some of the examples I probably want to look at with you guys for the rest of the course probably involve this, because a chief example of an unbounded operator on a Hilbert space, I think the derivative operator is such a thing. Yeah, if you look at page 207, example 4.11.13, to consider the operator A equals I ddt. He's like, it's not, I guess it's not self-adjoint. And it's also, I think that's unbounded from what is it unbounded? I'm just hoping it's an unbounded example because this is the section on unbounded things. He didn't say it's not bounded, did he? I remember in my reading, though, that the derivative operator is not bounded. I'm not seeing it at the moment to prove to you guys. Anyway, as you know, our semester is finite. Something has to give, so I'm moving on, all right, to greener pastures, if you guys don't mind. So.
I've been waiting for this differential equation.
You've been waiting for the differential equation for a while? Yeah, so let's get into it. I think I still have sufficient energy. If you guys have sufficient time. Okay, cool. I believe my son's baseball game has gotten rained out. So, yeah, you know, I have more and more appreciation for this book. Like, I know I can learn so much more if I just invest, you know, a couple 100 more hours just working through this book. There's so much. And, man, to have time to work out the homework problems, I'm jealous. You guys get to work some of the homework problems out. Sadly, I do not have time for such frivolity in my current schedule. Who knows? We may be in the situation where this place we start offering that masters in math, and then maybe I could actually teach this for reals. Not yet. We have masters. We have master's programs in all kinds of things. There is I think we may already have like a master's of arts in teaching, but I think it's probably through like the, well, I suspect Liberty already has something that's kind of like, actually I'm not sure even about that, Audric. I'm not sure Liberty even has, like West Alabama has, with that kind of like, yeah, is it a master's? Yeah, kind of, sort of. Oh yeah, what you're in.
No, absolutely, yeah. It's called adult continuation.
Adult continuation. Okay, so, all right.
A lot of people are asking me like what I'm doing this semester because they saw my file, I graduated, and I said, well, I'm just competing right now and taking some math classes at Liberty. Because, well, I go to West Alabama. Let's be honest, I am a Liberty student.
that is true. Yeah, fair enough. So,
they're going to send my Nagel, Snap, and Snyder home. Am I going to need to reference Nagel, Snap, and Snyder?
Do you have it?
I know. I took it home when I was home.
Oh, okay, but you do have it at home. But
yeah.
I mean, if you had it, that would be helpful. I don't have one with me. So I'm a teaching from the heart. So let's get to it here. So listen, for the most part, when you take differential equations, we talk about what are called initial value problems. So initial value problems are easier because basically all of the data for the problem is given at one value for the independent variable. And so we have very nice existence theorems for initial value problems. I think so. In contrast, boundary value problems, you're given information about the solution at two different values of, let's say, time or position. And you're trying to find a solution that has the same feature or a given feature at two different values, typically. And this makes it a boundary value problem, and it makes the structure of the solution sets really different. So let me just look at an example. If we have something like, let's say, y prime prime plus, yowzers. Well, I'll keep it simple. Y prime prime plus y equal to 0, all right? With, let's say, y of 0 equal to y of L, all right? Then we can ask, what are the solutions? This is an example of a boundary value problem. So how do you solve this? Well,
Characteristic equation?
yeah, pretty much. So the, we get differential equations, all right? Let me just say that. Tells us that the solution y has the form C1 cosine t. Well, let's say this is an x, all right? So C1 cosine of, you could use x, you could use t. I used prime prime, so who knows, right? Plus C2 sine x, right? All right. And then, so y of 0 is what? It's C1, right? And, I think I want this is equal to 0. Sorry, as I said, I'm teaching you from the heart, so my heart
do you
first.
want complex solutions? Because wouldn't the characteristic equation be r squared plus 1?
Well,
That-
sure, and yeah, e to the ix is the complex solution. The real part of it's cosine, the imaginary part sine. We're looking for real solutions, so
Okay.
we use the real.
Same thing,
Yeah, it's the same thing, but we'll keep it real. And my apologies. I'm not sorry. So C1 equal to 0. Okay, there we go. Woo. And y of L is what? Apparently C2 sine of L. Well, sine of XL, right? And you thought we wouldn't use XL in this class.
What, is L an operator?
Sorry, this differential equations kind of made me giddy. The dad jokes are flowing from me freely today. What's that?
Is L an operator? Yeah, what is-
Nope. L is a length.
Oh.
Yeah.
So X.
XL. Yeah, oh, my bad. You're right, I should just have L there.
Okay.
Yeah, I'm a dummy. I see your confusion. It's because that was wrong. Although it did allow me to make a stupid joke, so I have no regrets.
It is worth it.
Audric has left the building. No, it's here. Anyway, so question,
Headphones died.
what can you say about this? So either C2 is equal to 0, and if C2 is equal to 0, you got nothing. Nothing, right? Or,
L is pi.
yes, or L is equal to n pi. So without loss of generality, we can assume that n is a natural number. Why? Sine is odd, right? So if we used integers, we would be getting the same solution 2 times.
Okay.
So, behold, yn of x equals to sine of, let's see here,